You're the guy who's just been given the nod to find out why the production line has come to a screeching halt. The operator reports an HMI flashing fault reading Emergency Stop Active. Here's the interesting part. There are 3 e-stop buttons at different locations along a 10-meter conveyor system. You know from experience that the 3 switches are wired in series, and the fault alarm can't tell you which switch is causing it. Newer machine designs use separate safety inputs for each e-stop, but for a number of reasons, your plant does not use them. Well, you could apply the least effective shotgun method for troubleshooting and head out to the plant floor with a bucket of new switches to replace them all. Or use a proven logical troubleshooting method that we'll discuss in this video. Let's start with a discussion on what an e-stop switch is and what it does. An emergency stop switch is a manually operated switch that instantly stops a machine and places the process in a safe state when a perceived hazard is present. Even if the hazard is removed, the process won't restart until the e-stop is manually reset. For safety reasons, an e-stop switch is normally closed, or NC. Why? With a normally closed switch, voltage is normally present throughout the circuit, providing proof of circuit continuity. If an open circuit occurs due to a broken wire or a defective switch, it is detected quickly. If it were a normally open or NO switch, power would be applied only when the switch is operated. An open circuit fault would not be detected until the switch is operated, which is unacceptable for obvious reasons. Keeping your maintenance team trained on electrical safety and troubleshooting can help reduce downtime. With Realpars Business, your team gets access to a full library of industrial automation courses. Visit realpars.com/business to learn more, fill out the form, and book a call with our team. Okay, let's get back to our 3 e-stop buttons at different locations along a 10-meter conveyor system. In a perfect world, the switches are not exposed to physical damage, like being struck by pallets. But most of us don't live in that world. So, the first step is to walk the line looking for visible damage. When none are found, we revert to actual electrical troubleshooting. Anyone who has studied series circuit theory knows that a break anywhere in the circuit instantly stops current flow. So, operating any of the series wired e-stop switches will trigger an emergency stop active alarm. But any switch failure or open wire can cause the exact condition. Time to do some troubleshooting. Let's start with our preferred live voltage troubleshooting method rather than the awkward continuity or resistance testing method. We'll start by setting our digital multimeter, or DMM, to measure DC volts. Let's assume our power supply voltage is 24 volts DC, and we can connect the black lead of our DMM to the circuit common, or 0 volts DC. Our second assumption is only valid if we have very long DMM leads or can use additional wire to extend them. The troubleshooting process involves using the red DMM probe in a series circuit to pinpoint the exact point at which the 24 volts DC disappears. You could start at the power supply or at the sensing end. Seasoned troubleshooters will tell you to start in the middle, thereby eliminating half of the circuit right away. This is called the divide and conquer half-split method. It cuts your troubleshooting time in half by confirming the correct operation of half of the circuit. Of course, this sounds great on paper, but it boils down to not having to crawl on the floor or perform Houdini-style maneuvers to place the red DMM probe where you want it. Okay, let's do it. We clamp the DMM black probe to the 0 volts DC common point on the PLC. We place the red probe on point B. If you measure 24 volts DC, everything up to and including S1 is fine. Let's split the circuit in half again and place the red probe on point C. If you measure 24 volts DC, it proves that S2, S3, and the associated wiring are fine. Let's assume you measure 0 volts DC. Aha! That reading indicates an open circuit between points B and C. It could be S2, S3, or a broken wire or a bad connection. Now it's a matter of taking voltage readings at points D and E to pinpoint where the 24 volts DC disappears. Let's assume you measure 24 volts DC at point D. That measurement would lead us to conclude that S3 is open, which is a pretty solid assumption. If you're a bit fuzzy on why the 24 volts DC seems to disappear and why it appears across the open switch, it has a lot to do with the very high input impedance of your DMM and a fundamental principle known as Kirchhoff's voltage law. If you're curious, research Kirchhoff's voltage law. Okay, back to our conclusion that S3 is faulty. Based on our findings, you'd be pretty safe replacing S3. Wait a minute though. Before replacing the switch, inspect the terminals carefully. Loose terminal screws and broken conductors are common culprits as well. But why don't we perform a final conclusive test on S3 using our DMM set to measure ohms? Why didn't we start with resistance measurements? Ohm meter measurements require that you remove power and isolate the component under test. Power removal is usually easy, but isolating the component sometimes involves difficult wire disconnections. Live circuit testing is easier and just as conclusive as resistance testing. Okay, let's assume you've removed the power supply and followed your plan's lockout-tagout or LOTO procedures. Disconnect at least one wire from S3's terminals. Connect the DMM probes directly across S3's screw terminals. Not surprisingly, the meter displays open load, or OL. Some people will tell you to use the DMM's convenient continuity feature, which gives a beep for continuity and silence for an open circuit. That test is certainly valid in our example. As a point of caution for other continuity measurements, don't assume the beep indicates a 0 ohm condition, as many DMMs will produce a beep even if the measured resistance is as high as 50 ohms. If you rely only on the beep, you might incorrectly assume a device under test is functioning properly when it actually has higher resistance than you conclude, leading you away from the real issue. At the end of the day, regardless of how smart your PLC is, traditional skills in voltage, resistance, and continuity measurement are an asset for locating the defective switch or wiring fault. If you want to improve your electrical maintenance skills, check out our Industrial Electrical Maintenance Essentials 1 course. In this course, you'll learn how to work safely, inspect electrical systems, and troubleshoot common electrical problems. Find the link in the description below. And if you're looking to train your engineering and maintenance teams, Realpars Business offers practical courses on industrial automation, electrical systems, PLCs, and more. Learn more at realpars.com/business or use the link in the description below.